Okay, so I did want to come back in, and before I show you the key to the homework, just talk a little bit more because I was kind of right at the end of the last video for my 15 minutes. But this integral notation over here is super important for making sure that you understand kind of what's going on here. So just like when we were doing the limiting process for derivatives, we switched from the limit notation for derivatives to the actual derivative notation. We're doing the same thing here. The limit of a sum of rectangles, regardless of which endpoint you use, is a limiting process if we let the number of rectangles go to infinity. So the definite integral, okay, which is going to be related to the indefinite integral that we did earlier in the first set of notes that I did for Unit 6, but that this integral notation is going to be something that basically represents the net area or the net accumulation. So two things that you want to pay attention to. You definitely need to know the upper bound, and I'm not sure if y'all can see my mouse, so let me change to a highlighter here. Let's do pink. That the lower bound and the upper bound, that when we take a look at those two things there, that those come from the interval A to B, and that was a little dark, so let me change to the lighter one, from the interval from A to B that we had up here. So you kind of need to know in the context of the problem what your interval is. So you sometimes can tell over here, but the problem with like the delta x that you have over here, remember that delta x is equal to b minus a over n. So if in your summation notation you have something like 6 over n in that location, then that is going to tell you what the difference is between A and B, but not necessarily what A and B is. So you do want to make sure that you read the problem and you look for what your interval of integration is going to be from that given interval. The second thing to notice as you're looking at it is that your f of, change to a different color, this f of x sub I over here, that function is going to be the function that you put over here in your integrand. And you do want to remember that that is called the integrand. And so the height of the curve or the rectangles that we're getting from the curve itself is going to be the integrand. And so it doesn't really matter left endpoint, right endpoint, midpoint, and so on. But we do want to recognize that the function is going to go there. And then the width of the rectangle, the delta x, and the dx, which remember is our differential form of the derivative, that dx represents the width. And remember that dx as the differential is this idea of the width going to 0, and that's where that limiting process comes in. And so that will tell you what variable you're integrating with respect to once we start showing how the indefinite integrals that we did earlier are going to be related to this definite integral. But for right now, we just need to recognize that these two things represent the same quantity. All right, so let's come down and let's talk about the first problem. So our first problem here, we have that the snow starts falling at 6 a.m. The rate that the snow is falling overnight is represented by the equation S prime of t, where S prime of t is measured in inches per hour, and t represents hours since midnight. Now, I highlighted this because this, I think, is going to be something that you have to pay attention to. When I'm getting my quote-unquote interval for my bounds, what I have to recognize is that t equals 0 is midnight. But the snow didn't start falling until 6 a.m. And so when I ask for the total amount of snow during the first 3 hours of snowfall, you should not go 0 to 3 for your interval. Your interval is going to be 6 to 9 in this problem. And so that's why over here in my definite interval, when I was highlighting it, this is a 6 and this is a 9. Because that matches the bounds on the interval of time that we're interested in. Right? The function that we are doing the net accumulation under the quote-unquote velocity curve is going to be the S prime of t. So that goes into to the integrand when we're looking at it down here. Trying to match my colors that I used earlier. So there's your integrand, and then of course your dt is your variable of integration. Now, kind of as we're looking at this, excuse me, I did want to talk about a little bit about units, because when we talk about the units, this kind of can get a little confusing. But remember, the units of s prime of t is going to be in inches per hour. And remember that the delta t, or the change in t, is going to be in hours. And we're summing up, remember this is the limit of a sum. So we are summing up basically the height of the rate function, the height of the velocity curve, times the width of the velocity curve, and that is going to give us a total unit that is going to be in inches, because this is the sum of the area, which is inches per hour, times hours, which is going to be in inches. So whatever this equals, when we calculate this out, the units of this would be inches. And it is the net change in the amount of snow that has fallen, because we're looking at the quote-unquote velocity curve, the derivative curve, and the area under the derivative curve is going to give you the change in the original function. So this would be the amount, the displacement between how much snow you had at 6 a.m. to how much snow you had at 9 a.m. Right? During the second problem that we have here, again, c prime of t is a rate, and that's in bars per minute. So let's kind of add our units on. Bars per minute times minute, because our delta t dt is in minutes. And then we have this limit of the sum that we are adding them up. And we're adding them up on the time interval from 0 to 9. So 0 to 9 minutes would be our interval of interest here. And so during the first 9 minutes, we had 46 chocolate bars were removed from the shelf. Now, how do I know it was removed? Because they told me that. If I was doing this in a problem and saying what the rate is, technically, if we're talking about graphing this, I guarantee you that this rate function, because we're removing them, is going to be below the x-axis. And even though it's not a negative number here, when we are talking about it, we would be kind of interpreting what we see on the derivative graph. So if I was kind of looking at this, it's probably that from 0 to 9, your c prime of t is going to be running below the quote-unquote area that represents here from 0 to 9 is going to be an area of 46. And we know that it's being removed because c prime of t would have been below the x-axis as you're looking at it. So that's kind of one idea when we start talking about, there's a difference of when we talk about area versus net area, because area would be positive 46, because area is always positive. But when I talk about this net area, the net area would be negative 46, because we took away, that we are not accumulating, we are taking out for this function. So those are some things that I do know about this function c prime of t. Number 3, taking a look at it, there will be lots of what I call multiple choice questions where you are taking the limit notation and telling us what is the integral, definite integral notation that goes with that. So again, looking at this, the function that gives the height is the f of x sub I, and in this notation, they just have it as x sub I. Notice that over here, there is no x sub I, because it doesn't matter what endpoint you use. It doesn't matter if you use the left endpoint or the right endpoint, because when I do the limiting process, they all collapse down to exactly the same point. So you'll notice that the x sub I part drops out, and we just simply write what was the function that we had. That's our integrand, and remember that that represents the height of each rectangle. And then the dx over here is what we did when delta x went to 0. It became that differential, and that is our width of the rectangle. The integral notation is our sum limit of a sum, and that's why it became the definite integral. And then where did our bounds come from when we were looking at it? Remember that the bounds always come from the interval of interest, the -2 to 7 on that, right? So then we look down at 4, and now 4, we're basically estimating. Notice that they want to use a right Riemann sum to approximate a definite integral. So what you have to recognize now is that the definite integral is really just talking about the area under the curve. And the curve that we're doing the area under is this r prime of t. So that's my function. That represents the height of the rectangles that we're adding. Whereas t, of course, and the delta, I said delta x in my key, but I'll change it to delta t because they change in t. Now remember that in this, kind of as we're looking up at it, the 0 to 12, I just want to highlight that because they'll do this to you sometimes. Make sure that your table does not include extra values because you would not use them. Make sure that you only go between the beginning of 0 to the end of 12. We want 5 rectangles. So notice that as I was highlighting it out, I was like, okay, where are my 5 rectangles? Here's rectangle 1, 2, 3, 4, and 5. The beginning and end of each of these is kind of representing your left endpoint and your right endpoint, say for that first one. So pay attention to what you're doing, and that this is a right Riemann sum. So we want to make sure we're using the right endpoints. And the right endpoint of the first one is going to be the 2, and the function value is going to be the 4. The right endpoint of the second rectangle is 5, and you're using the function value of 2, and so on. So notice that my Riemann sum, and when you do this on the AP, you must show a Riemann sum. You can't just go to the answer. So it's like showing the difference quotient when you're doing a derivative estimate. For a definite integral estimate, you must show a sum, and the sum must have a width times a height for each of these that are there, okay? Notice that each of these has a width times a height. Don't simplify them. The second thing is, notice there are 1, 2, 3, 4, 5 in the sum because there are 5 rectangles. And then, of course, you would just add it up and get your answer for that. And then in terms of interpreting it for our final part of this discussion of this set of problems, our net change in the radius is what this definite integral is calculating. It's also the net area. We could also kind of talk about as the net area under r prime of t, which is our velocity curve or our derivative. And that it's basically just telling us how much there was a change in the amount of the radius. Remember the radius, we're talking about r of t, so it's the net change in r of t. And that means it's the net change in what the radius was at the beginning, 0, to what the radius was at the end, 12. So what our kind of real world, what we would say is that during the first 12 minutes, the radius grew by 19.3 feet. Okay, I hope this answers all of your questions about the homework. If you have any questions, shoot me an email. We're going to go on to the next set of notes, which has to do with more looking at these definite integrals as limits, because that's going to be important to be able to switch from limit notation to definite integral notation and vice versa, right? So we're moving on to the next video.